Good morning, everybody. Welcome to class, even on Saturday. So, as I explained previously, this class, CS4347, is about building bridges. In the first week, we talked about the bridge between analog and digital domain, or analog and digital world. And we human beings do live in the analog world, so everything we hear or we see are analog signals. In order to process these kind of signals, we have to transmit or convert these kind of analog signals into digital domain. Therefore, we talked about some fundamental theorems to actually convert this signal between these two domains. For example, there is a Nyquist sampling theorem. It tells us the lowest frequency that we have to do to sample an analog signal to digital domain. Can anybody tell me what is the content of the Nyquist sampling theorem? Correct. This basically tells you the minimum sampling frequency in order to feasibly to reconstruct the original signal. Then, in the second lecture, we talked about the bridge between time and frequency domain. In particular, we discussed about the discrete Fourier transform, in short, DFT. Okay, that is so important that we actually spend quite a lot of time to explain what is the intuition about this transform. Okay, so for the third lecture, means today, we are talking about a bridge between frequency domain representation and a perceptual domain representation. Okay, so that's about the third lecture. We are going to go to the third one, perceptual domain features. And for this particular lecture, we are going to have a review of the perceptual analysis, and then followed by the perceptual features. Okay. Now we are talking about the review of the time and frequency domain resolution issue. That is such an important issue that it deserves some more discussions here. We are talking about the time resolution and frequency resolution. So can anybody tell me what is a time resolution? Malaysia. Do you still remember from this hint here?
It says the signal, the time during which a signal is observed.
Very nice. So, okay, that is of course the definition. I need you guys to really have a deep understanding so that in any practical situation you will understand what is the time resolution and what is the frequency resolution then. Can anybody volunteer? Carl.
Well, I'm not entirely sure.
Okay. This is already the definition here. I already tell you what is a frequency resolution. But in practice, I wanted to emphasize it again. Last time, do you remember this equation? This basically tells you the DFT, discrete Fourier transform. Mathematically, this is just a simple equation. We have this time domain signal xt, and we have the frequency domain representation capital Xk. Correct? Remember, we spent a lot of time to do that, and then we use this simple equation to map a time domain sequence. This we call capital X, small xt. And then we map these to the frequency domain representation capital Xk, correct? for example, we have 8 samples here. We map this thing to this unique circle like this, because this is the real, this is imaginary. Correct? So we map these time domain samples to this one. What does it really mean? Means in this time domain, we get rid of everything in between. In digital domain, basically, only these samples exist. Remember? That's why we can very flexibly process this time relationship between samples. Do you still remember that if I play back these sample using a different sampling frequency, how does it sound like? Correct? And then the trick here is that we map these discrete time samples to the frequency domain like this. Assuming that we have 8 samples, time domain samples here, we are going to have 8 samples here. What does it really mean? These samples here covers the entire sampling frequency. So in this case, assuming that we have a sampling frequency of 8 kilohertz, okay, that's why I want you to understand this, not simply memorize what I defined here. So assuming that my sampling frequency is 8 kilohertz, I have 8 samples here. What is the time resolution? Can anybody tell me? Jonathan. I said my sampling frequency is 8 kilohertz, not here. This is my sampling frequency. In fact, 8 kilohertz is a real sampling frequency that people use in digital telephony. Okay? So I have 8 samples here. I'm asking you, what is the time resolution? What is the frequency resolution? You need to wake up to do a very simple computation. Anybody wants to volunteer?
8 samples at 8 kilohertz, so that means between each sample there's a 1/8,000 second delay.
No, I'm talking about the time resolution. A very simple definition here. 8 samples. What is the duration of these 8 samples?
1/8,000.
I'm sorry?
Oh, the 8, all the 8.
Correct.
So that's 1 millisecond.
Correct. That is the correct answer. Then what is the frequency resolution then? Yihan?
It's the first divided by sample.
I'm sorry?
It's the first
Please be loud.
It's the first divided by the number of samples.
Well, I need a concrete number here. I'm asking you, what is the frequency resolution? In this concrete case, my sampling frequency is 8 kilohertz. I have only 8 samples here. What is the frequency resolution? Is that so difficult?
And it's like 8,000 divided by 8.
Divided by 8, and that is 8,000.
1,000.
1,000. Then what does this 1,000 really mean? That is actually what I'm trying to ask you guys. So, Johnny, is that correct pronunciation? Johnny?
Yeah.
Right. So what does this 1 kilohertz or 1,000 hertz mean here? This is my frequency resolution, am I right? Okay. So meaning, remember last time when we talk about this DFT, so in this case, basically the frequency is a DC component. Here is something slower. This is actually even faster. That is, do you guys still remember? So any, according to the definition, so any periodic signal can be decomposed to a summation of sinusoids. And that's what actually this Fourier transform about, correct? But the problem is that here the arbitrary sound can have a frequency component anywhere. But the problem here, according to this definition, we can only map to this kind of frequency we define here. Okay? So particularly if we divide this by 8, the frequency resolution is 1 kilohertz, correct? 1 kilohertz, 2, 3, 4, 5. Is it correct? Yes or no? How many samples we have here? No. We have more, right? If we divide it by just 8, 1, 2, 3, 4, 5, 6, 7, 8. Correct? So basically, meaning I will be able to represent this is 1 kilohertz, 2 kilohertz, 3, 4, 5, 6, 7, 8. Back to the original. Correct? So if I have frequency component in between somewhere here, what happens? So these are all very practical questions. You don't have to memorize the definition because in real life, remember, in the second lecture, I gave you some example. Sometimes if you do perform this DFT computation, you can get a very sharp spike without anything in between. In what kind of situation this happens? Do you guys still remember how I explained what is the intuition of DFT? I have an unknown signal. I'm going to actually do the multiplication of these sinusoids here, correct? The coefficient, if the coefficient is big, what does it mean? If I have a sinusoid exact matching these sinusoids, then if I sum these numbers together, this will be big. Do you agree with that? Yes. So exactly the situation. Now I'm asking you a question. So if we have a frequency, for example, in this particular case, 1 kilohertz, right? We are going to have a very sharp coefficient there, nothing else. But if, let's say, we have a frequency component like 500 hertz. So if you compute this DFT according to this equation, what happens? That's my question. Can you guys have a guess? In fact, in my second lecture, I already gave you some examples. You already know what really happens. Correct? So if I have a component like this here, so do you think that because we are not going to match any of these so-called basis function here, so then what is the result will look like? Think and wake up. So, Hans, so do you think that you can have a good guess here? Or, well, Ari, what do you think? I'm saying that my grid is just a discrete sinusoid signal here with concrete frequency here annotated. But my input signal has a different kind of frequency, in this particular case 500 hertz, right? So I'm asking you, when you compute these DFT coefficients, what does it look like? Is there going to be something big here, something big here, or something big here? That's my question. And in fact, you could do this computation by yourself because this equation is here. And after you compute this, well, you will get these frequency coefficients there, correct? We are talking about the similarity between your frequency in the signal and matching this basis function. That is a simple sinusoid signal there. Remember still? Okay. If you have not done this, try this by yourself and then tell me your results. Okay? So that is, I'm just kind of explain to you why we are talking about a bridge. We are bridging this time domain signal to frequency domain. Okay? Think about that. And we have also a very clear definition what is the time resolution, what is the frequency resolution. Okay? If we want to have a very good time resolution, the price to pay is that we are going to have a quite lousy frequency resolution, correct? If we want to have a very good frequency resolution, we have to increase the duration, meaning we will have to lower the time resolution. In this case, we are going to have a much denser representation in the frequency domain, correct? The gap between is going to get smaller. Is this clear? Very good. So now the symmetrical property of the DFT, you can see if we plot the DFT from an audio signal, typically it looks like this. In this particular case, the sampling frequency is, let's say, 2000 hertz. Then the symmetrical point is there is just 1000 hertz. Okay, so basically we can use only the lower half that is going to be sufficient. Another thing is about the domain duality. You remember, and then we can plot the signal in the time domain. We can also generate a spectrogram. Remember this animation we did? So this is the time, this is frequency. This red color represents higher amplitude in the lower frequency range, and here this blue one means it's lower. You can imagine that it's almost like a 3D representation here. Okay, the color represents the strength. We are going to actually regenerate this spectrogram a bit so that you will understand this better. Remember this animation that we cut these time domain signals and then do a FFT and rotate these to this frequency domain. That is how the spectrogram is generated. And then this duality, as you probably remember, a pure tone, a pure sinusoid signal looks like this. In the frequency domain, it should like this. It's just a one sinusoidal signal here. We can use 3 parameters to represent this sinusoidal tone. What are they? Joe. Amplitude, frequency, and phase, correct? Yeah, so these are the 3 parameters so that we can uniquely determine this sinusoidal signal here, okay? All other basic signals, like the square wave, like the train of a pulse, like a single pulse, and then like white noise. And white noise meaning in the spectrum frequency domain, it is a flat spectrum. Okay, and then also a short tone burst like this, and then we have a nice frequency domain representation like this. And then also the duality, talking about how do you do the convolution. Okay, in the time domain signal, and if you do this sinusoidal and plus this window function, do a convolution, we are going to modulate this representation to this kind of representation. Okay. Another important phenomenon that we demonstrated last week is also about this aliasing phenomenon, meaning if our sampling frequency does not satisfy the Nyquist sampling frequency, the theorem, so what happens? You remember this violin song, right? This will be totally distorted and mapped back to the lower frequency. Another thing is why this overlap at is important for audio processing. So how many of you actually have taken courses like in computer vision, something like this? Raise your hand, please. Okay, so some of you have done, right? So you probably know that in video processing or analysis, typically this big picture is going to be divided to this matrix, these smaller blocks there. And then you can also do like DFT to transform this to frequency domain and process that. The point is that can we do the same thing for the audio signal? That means this is my audio domain samples, right? Can we do this block processing without any overlap? Of course, this is an important thing, in particular for the compression kind of application. For analysis, sometimes this kind of processing is still acceptable for analysis. Remember, if we do this kind of block processing, especially if we do this DFT, convert the time domain signal into frequency domain, if you don't do anything, immediately transform the DFT coefficient back to time domain, then you can perfectly reconstruct the original time domain signal. But if you do anything in the frequency domain, touch anything of these coefficients, this capital K, xk, then we will generate a interesting phenomenon called block effects, meaning the discontinuity between blocks. This will make this sound very unpleasant. So therefore, for audio processing, typically this overlapping window is very much used. Okay. This kind of a block effect, and you can see, okay, for the video compression or image compression, if the bit rate is very low, you can clearly see this kind of block effects, and then this picture is a low resolution picture, and I don't know has anybody seen this kind of phenomenon, but with audio signal, this kind of block effects can basically render the audio very useless. And then we talked about the common approach about the windowing function and overlapping. We have this so-called hop side when we hop the analyzing window from one step to the next one. And of course, this hop side could be short and long. And the maximum situation is that you can actually jump even over, leaving some gaps in between. That is possible, but you will definitely lose information. So this is because it's a review and a recap. And then if you guys have any questions, please do raise your hand. I try to do this quite quickly so that you understand what we are talking about. Building this kind of bridge is not an easy task. Okay. This is the framework analysis and synthesis, assuming that we have a audio signal recorded with a microphone, and we have this kind of overlapping windowing process. We do this DFT, discrete Fourier transform, and then after this step, we have these DFT coefficients here, right? If we do anything to process this, and then afterwards convert these back to the time domain using a inverse discrete Fourier transform, we have the time domain samples. We also do this overlapping and adding operation, hopefully, to get a faithful reconstruction of the original signal. That is a very rough description, for example, how MP3 technology works. Okay? But that is not a state-of-the-art technology. If any of you are interested in this kind of technology, and we can talk about this later on in the second half. Okay? And I have worked with this audio compression technology for quite a number of years, so I know a lot of details about that. Okay? So then we talked about the standard spectral domain features, so like the spectral centroids, and to describe the brightness of the sun. Of course, these kind of features are all handcrafted features, so-called. But these handcrafted features are very useful because it is easy for human beings to understand. Okay? And in the era of deep learning, and we cannot always rely on the deep learning. And I'm going to discuss this with you as well. For example, in this case, if we compute according to this equation here, we can hear this sound. With this feature, one is higher, one is lower. You can clearly distinguish how bright is this sound, correct? Okay. So, as I say, with these kind of handcrafted features, you can simply compute like this without any machine learning algorithms here. Okay, it's a very easy thing to do. And the other feature we talked about is the spectral roll-off, and another one we could this spectral flatness measure. In fact, this measure was commonly used in audio compression algorithms as well. So to see how flat is the spectral representation, and these kind of measures will be determined to devise the compression algorithms. Then the peak to average ratio here is also an easy kind of metric to compute. You can remember this. That is with quite a high peak to average ratio, and this one is quite low. So with these kind of features, we can distinguish different kind of sounds. Okay. Then we also talked about the spectral flux. In fact, that is an interesting feature as well. Remember this. Is quite high spectral flux, and this one, I'm sorry, this one is quite low. What happens? My goodness, this computer somehow stuck, not responding. Let's see. Close. Sorry for these small problems here. Maybe